Earthquakes are one of Earth's most dramatic and destructive phenomena. Imagine giant puzzle pieces that make up Earth's outer layer, called tectonic plates. When that stress finally overcomes the friction holding the fault locked, the fault suddenly slips, releasing a burst of energy in the form of seismic waves that shake the ground we live on. This includes studying the structure of fault zones, how faults interact through stress transfer, and the material properties of the fault zone, particularly within the slipping zone. There's often a central fault core that can be tens to hundreds of millimeters thick, sometimes made of very fine-grained material called ultra-cataclysite, possibly clayey. This damage zone is highly fractured and granulated, and because of its porosity, it's usually saturated with fluids. This refers to how the fault strength drops dramatically during the rapid slip that occurs during an earthquake. This topic has received special attention recently due to new theoretical ideas and experiments designed to simulate the very high slip rates seen during earthquakes. Several competing physical mechanisms contribute to this dynamic fault weakening during rapid slip. One is frictional heating, caused by the If enough heat is generated in a thin slipping zone, the temperature could rise dramatically, potentially leading to melting of the rock and the formation of a glass-like material called pseudotachyllite. However, evidence for widespread pseudotachyllite in mature faults isn't as common as the theory might suggest. This happens when fluids, like water, trapped in the fault gouge are heated rapidly by friction. Since fault strength is often related to the effective normal stress, the difference between the normal stress across the fault and the pore fluid pressure, this mechanism is considered a strong candidate for explaining why melting might not be pervasive at shallower depths, as it causes significant strength loss over relatively short slip distances. Experiments and theoretical models suggest thermal pressurization, possibly combined with other effects, can explain estimated earthquake fracture energy and rapid strength loss. The effectiveness of this mechanism depends heavily on Even if the overall slip zone is thin, the actual contact areas are much smaller, leading to intense localized heating at these tiny spots as they slide past each other. Laboratory experiments at high slip rates are consistent with this predicted friction reduction. Think of rubbing your hands together slowly versus very fast. The fast rubbing generates heat much quicker at the points of contact. Mechanical lubrication can also contribute to weakening. This might involve phenomena like the formation of silica gel. If silica-rich rocks are present and water is available, rapid grinding during slip can produce fine silica particles that form a low-viscosity gel, essentially lubricating the fault. This gel can maintain low strength under continued shear, although its full range of activity and contribution during seismic slip are still being studied. While dynamic weakening during fast slip is key to the earthquake rupture itself, fault behavior at slower rates is crucial for the period between earthquakes, known as the interseismic period, and for how earthquakes start, or nucleate. This slow slip behavior is often described using rate and state friction constitutive laws. These laws capture how friction depends not just on the slip rate, but also on a state variable that represents the history of previous slip and the maturity of contacts on the fault surface. The idea is that contacts strengthen over time when stationary or slipping slowly, perhaps due to atomic bonding or growth of contact area. This time-dependent strengthening plays a role in how stress builds up and eventually leads to the unstable slip we call an earthquake. Understanding the transition from ductile to brittle fault response, and thus the depth where earthquakes occur, the seismogenic zone, involves interrelated concepts. One older idea is a transition from localized friction to broadly distributed creep at depth due to increasing temperature. Where friction strength is less than creep strength, the rock is considered brittle and prone to earthquakes. A more recent concept proposes that the depth limit is set by a transition from potentially unstable localized friction, where increasing slip rate leads to weakening, allowing earthquakes, to inherently stable localized friction, where increasing slip rate leads to strengthening, preventing spontaneous earthquakes. Both concepts generally result in a temperature limit for seismogenesis depth and help explain why creep can occur below the locked seismogenic zone. To model large-scale fault rupture, scientists often use simplified frameworks. A widely used one is the slip weakening model. This model represents the idea that the fault's shear stress traction drops as slip increases during the rupture. It's characterized by parameters like the initial stress, the peak strength, yield stress, the residual strength, kinetic friction level, and the characteristic slip weakening distance, DC. This DC represents the amount of slip required for the traction to drop from peak to residual strength. This shear stress drop happens within a finite zone at the rupture front called the cohesive or breakdown zone. While simple, this framework is effective for modeling dynamic rupture. More complex constitutive laws, like rate and state friction, can sometimes be mapped onto or mimic this slip-weakening behavior, especially at the rupture front. Other complexities in fault dynamics include the effects of invariable normal stress, which can occur on faults separating different rock types or near bends and branches. Also, the material in the surrounding PC damage zone can deform inelastically as the rupture front passes, potentially interacting with the slip process in complex ways that aren't fully understood. Bringing laboratory experiments, which typically involve small samples and controlled conditions, to bear on massive natural faults presents challenges. Scientists aim to determine the fundamental constitutive response of fault materials in the lab. The hope is that these local responses, measured at scales much smaller than a whole earthquake, are directly applicable to natural faults without needing arbitrary scaling. The challenge lies in integrating these small-scale constitutive laws into large-scale models, especially when computational limitations require using larger than experimentally justified length scales for parameters like the characteristic weakening distance. Beyond understanding the fundamental physics of how earthquakes happen, humans have long sought to predict when they will happen. The U.S. Geological Survey, USGS, is quite clear. Earthquakes cannot be predicted. A true prediction requires specifying the date and time, location, and magnitude. No scientist has ever successfully predicted a major earthquake in this way, and the USGS doesn't expect this to be possible in the foreseeable future. Claims of prediction are often dismissed because they lack scientific evidence, fail to define all three required elements, or are so vague they're guaranteed to fit some earthquake somewhere. Historically, people have tried many imaginative methods to predict earthquakes. Ancient Chinese used a vessel with metal dragons and balls. A shaking ground would make a ball drop from a dragon's mouth, indicating direction. Talk about low-tech seismology. Even animals have been observed behaving strangely before quakes, with stories dating back to ancient Greece. Rats, snakes, and insects reportedly fled areas before a destructive earthquake in 373 BC. While anecdotal evidence abounds, consistently reliable animal behavior and a scientific explanation remain elusive. Apparently, even a metal dragon might beat relying on your cat's mood swings. Other attempts include monitoring radon gas emissions, which might spike before a quake, but widespread, reliable correlation hasn't been found. Stories of strange earthquake lights exist, and while recent research suggests a possible physical mechanism involving stressed rocks, these lights are rare and not useful for prediction. Measuring electric signals in the ground, like the Van method, has also been attempted, with some claiming success, but critics suggest results could be due to chance or even mundane sources like perhaps a trolley car depot firing up in the morning. The idea that planetary alignments or tides, syzygy, could trigger quakes has also been explored, but again, no statistically significant, widespread correlation has been found. More recently, researchers are exploring new avenues like using artificial intelligence, AI, to analyze seismic data. A team used AI to analyze acoustic and electromagnetic data from a monitoring system in China and claimed to correctly predict 70% of earthquakes in a specific area a week in advance during a trial. This was achieved using existing AI techniques and a rich data set. While promising, even the researchers admit this needs rigorous testing and replication in other seismically active regions, which may be challenging due to differences in data availability and earthquake patterns. The USGS views this work as a proper first step in vetting a possible prediction technique, but emphasizes it's too soon to call it a breakthrough. While predicting earthquakes remains a distant goal. Earthquake Early Warning, EEW. Systems offer a practical way to reduce risk. EEW is fundamentally different from prediction. It doesn't tell you when the next earthquake will happen, but it alerts you, after one has started, that shaking is on its way. These systems work because seismic waves travel at different speeds. The first waves to arrive, called P waves, are less damaging than the later, stronger S waves. EEW systems use networks of sensors located closer to the earthquake's epicenter to detect the initial P waves, quickly estimate the quake's location and magnitude, and issue alerts before the S waves arrive at more distant locations. Systems like the Shake Alert R EEW system for the west coast of the United States are examples of this. Shake Alert uses a network of seismic sensors, high-speed computers, and rapid communication pathways to generate alerts. These alerts can be sent to people via cell phones, prompting actions like drop cover. The goal is to provide precious seconds to tens of seconds of warning. The success of EEW also depends heavily on people's ability to receive and respond to alerts. This involves significant effort in communication, education, and outreach, often involving social science research to understand how different populations understand alerts and what actions they will take. Making these systems accessible and understandable for everyone is a critical challenge. In summary, scientists are continually deepening their understanding of earthquake mechanics, from the complex rheology within fault zones. While reliably predicting the timing of earthquakes remains elusive, research into promising new approaches like AI continues. Meanwhile, earthquake early warning systems represent a successful application of seismic science and technology, providing actionable alerts after an earthquake begins to help people and systems take protective measures. The ongoing work in these areas, supported by geological observations, laboratory experiments, theoretical models, and crucial social science insights, continues to enhance our ability to prepare for and mitigate the impact of these powerful natural events.
Welcome to the world of geology and earth sciences with Ricardo Valls, a seasoned professional geologist bringing you over 1,500 videos of unparalleled expertise. Whether you're a budding graduate student, an early career specialist, or a seasoned professional, this channel is your gateway to a wealth of knowledge. Explore a vast array of Earth-related subjects, including geology, geochemistry, structural geology, and the application of artificial intelligence and machine learning in geosciences. Ricardo Valls not only shares his own invaluable insights, but also brings you exclusive interviews and collaborations with other prominent geologists, offering a comprehensive view of the field. Stay ahead of the curve with our latest content, covering everything from unraveling the Earth's secrets to exploring global geological phenomena. Don't miss this opportunity to enhance your knowledge and stay at the forefront of the industry. Subscribe now, hit that like button, and share this invaluable resource with your colleagues and friends. Join our growing community of over 2,000 earth science enthusiasts and professionals today. Unlock the secrets of the Earth with Ricardo Valls, your top resource for all things geology. The future of geosciences is here. Be part of it.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.